Our next example in 1.4 is an example in context. It says you are riding an elevator from the 10th floor of a hotel at a height of 150 feet down to the lobby at a height of 0 feet. The elevator travels at a constant speed, and you reach the lobby after 30 seconds. So part A is asking what kind of function would model this situation and how do you know? When we think about functions and what type of function would model a situation, we have to think about the rate of change. Since we are told that the elevator is traveling at a constant speed, that means that we are modeling this with a linear function because the change is constant. So now we need to write an equation for that function, a linear function, that would give you your height as a function of time. So height as a function of time here. When we look at a linear function, we need a y-intercept and a slope. Through reading this, I can see that my y-intercept is that starting height of 150 feet. And my slope I know has to be negative since I'm going down at a constant speed. My job is to figure out what that constant speed is. So I can use my average rate of change formula, change in y over change in x. I know that two of my x values are 0 and 30 from where I start to where I end, from 0 seconds to 30 seconds. At time 0, I'm up at 150 feet, and at 30 seconds, I'm at the bottom 0 feet. So when I do this subtraction, I get 150 over negative 30. 150 divided by negative 30 is negative 5. So my slope here would be negative 5 times t. Now my job is to restrict the domain for the values of t that make sense. I'm remembering that these t values are the seconds, and I reach the bottom at the lobby after 30 seconds. So I know that my t values can only exist between 0 and 30. If I look at this one step further, if I just look at this one side, this says that the t values are greater than or equal to 0. So time is bigger than 0, your starting point. And if I look at the other side, these t values are less than or equal to 30, meaning we didn't go beyond 30 seconds. So now I'm going to try to evaluate h of 6 and h of 40. When I evaluate h of 6, I see if it fits in my domain. The number 6 is in fact in between 0 and 30. So if I plug in the number 6, 150 minus 5 times 6, that would be 150 minus 30, which equals 120 feet. So at 6 seconds, we are at a height of 120 feet. H of 40, if I look at this number 40, 40 is not in between 0 and 30, so we cannot evaluate that one. It does not exist. As an extension to graphing lines with restricted domains, we get to this idea of a piecewise defined function. So when we read it, it says a piecewise defined function is a function that is defined for multiple pieces, each with a restricted domain. So it's like we're taking two separate lines and putting them together on one graph. For example, in this first one, I have this function f of x with two separate pieces. When I graph this, I'll graph 2x minus 1 for every x value less than 2, and then I'll graph y equals 5 for every x value greater than or equal to 2. So let's just look at this one piece at a time. If we start with 2x minus 1, that means our y-intercept is down at negative 1, and our slope is 2 up to right 1. And again, I'm just going to plot points as far as I can and restrict the domain after. Okay, so I've got all of the points along my graph, but I only want those points that are less than or equal to 2. So here's my number 2. I only want points, let me change colors real quick. I only want points that are to the left of that number 2. So I don't even want this first point because it's not equal to 2. So I might make this an open dot, and I'll connect all of the dots down below, going on forever. Okay. Now my other piece of this function is the number 5. When I graph the number 5, I just go up to my y-axis, 5 is my y-intercept, and I draw dots all the way across. Okay. But when I think about this, I only want that for the x values greater than or equal to 2. So again, if this is my number 2 on the x-axis, I only want to keep those orange dots for everything bigger than or equal to the number 2. So this dot would be closed since it does exist there, and we're only going to connect the dots to the right. Everything else is going to get erased. This is now my piecewise defined function. I have two separate functions, similar, but they have different pieces. One has a diagonal line and one just has a straight across line. So now my job is to use this piecewise function to evaluate f of 0, f of 2, f of 7, and f of 500. So when I look at this f of 0, I have to decide what piece the 0 fits in. So if I look here, here's where x equals 0, and that corresponds with my green line, or the 2x minus 1. If I look in my equation, I also notice that 0 is less than 2. So I would plug the 0 into the 2x minus 1 equation. 2 times 0 minus 1 equals negative 1. I would not plug 0 into the second equation because 0 is not greater than or equal to 2. So I'm only using that top equation. For the next problem, f of 2, we have to use our function to determine where 2 is. Is it in the green part or the orange part? So here's my number 2. And as I look up, it appears that I hit both the green line and the orange line. But I remember that the orange line is the one that's filled in. The green line is not. Because when I look back at these restrictions, x is greater than or equal to 2 for this orange part. So I would plug that number in here. Which is also a little weird because there's nowhere to actually plug that in. When we have a value that's greater than or equal to 2, our y value is just the number 5. So as we keep going, f of 7, well, that's certainly greater than or equal to 2. It just equals 5. And similarly with f of 500, that's also greater than or equal to 2, so that just equals 5 as well. If, let's say, for an extra example, I asked you to find f of negative 1. Well, we look and say negative 1 is smaller than 2, so I would plug negative 1 into that first equation and get 2 times negative 1 minus 1, which would give us negative 3. For the next example that we'll do, now we have 3 pieces of this piecewise function. So I'll start with the 4 plus x, and I'll color code it this time. So 4 plus x is going to be my pink function. That means that 4 is my y-intercept, and the invisible number 1 is my slope. So up 1, right 1, I'm going to go all the way across first, and then erase dots according to my restricted domain. It says that I'm only using 4 plus x for the x values in between 0 and 3. So if I start here at 0 and I end here at 3, I'm going to get rid of all of the extra dots that are outside of that. 0 gets a filled in dot, but this number 3 is going to get an open dot. And then I'll connect those. For my next piece, I'll make that orange maybe. I'm graphing a straight across line at 7 between the values of 3 and 5. So I'll make dots straight across at the 7. I end up overlapping there, that's okay. So all the way across, but I notice I only want those values between 3 and 5 on the x-axis. So here's my 3, here's my 5. I'm going to erase everything else, and I accidentally erased that important point. So since the 3 is actually included here, we're going to make that a closed filled-in dot. And the last piece of this piecewise defined function, maybe I'll make it blue, has the equation 9 minus 2/5 x. So 9 is my y-intercept, And my slope tells me to go down 2, right 5. 1, 2, 3, 4, 5. Down 2. 1, 2, 3, 4, 5. And if I had room, I would keep going. I only want x values in between the numbers 5 and 9. So I'll get rid of this one. And when I connect my dots, I notice that I'm kind of left in the middle here with an open circle. Okay, so we're only really taking care of those points. All right, so now I'm going to evaluate this function. I will start with g of 1. So if I look, my job is first to figure out where 1 exists. Is it in the pink part, the orange part, or the blue part? If I look at my graph, here's the number 1, and I notice that it hits the pink part. Additionally, the number 1 is in between the numbers 0 and 3. So I'm going to plug 1 into this first equation. 4 plus x, which is 1. So I know that g of 1 equals 5. The next one, g of 6. If I look at my graph, here's the number 6. That exists on the blue part of my graph. I'll double check that here in my equation. The number 6 is in between 5 and 9. So I'll plug that in. 9 minus 2/5 times 6. When I do that, I get 9 minus 2 times 6 is 12 over 5. If we wanted to do some more fraction work here, we could get a common denominator so that we can subtract those and get 45 over 5 minus 12 over 5. And 45 minus 12 is now 33 over 5, which also makes sense here on our graph. It's kind of a fraction in between some points. And lastly, I want g of 12. So I look and I see here's my 12, and there is nothing on my graph. Additionally, the highest number that I see in my equation is a 9, so 12 is actually outside the domain, meaning this value does not exist.